Good morning, y'all. All right, so yesterday we talked about wave properties. All right, so we talked about how whenever like the different types of waves, different types of classifications of waves, we talked about how if they require a medium, they're a mechanical wave. If they don't require a medium, they're called an electromagnetic wave. We talked about the difference between a longitudinal and a transverse wave. We talked about a pulse wave and a periodic wave. All right. We also talked about how frequency and period are still inversely related. And then we got a new equation, the wave speed equation. So we now know that wave speed can be found by multiplying the frequency times the wavelength. All right, but again, even though we can calculate the wave speed by using the frequency and the wavelength, remember that the wave speed is constant for mechanical waves in any given medium. All right, so it's not the frequency and wavelength that determine the wave speed, it's the medium that wave is traveling through. All right, so that's just catching us up from our last set of notes. Today, we're going to talk about, today's an easy day. All right, today we're going to be talking about wave behavior. All right, so we're talking about how waves behave whenever they come in contact with a boundary, and then how they behave whenever they come in contact with each other. All right, so if you have multiple waves that are happening at the same place at the same time. All right, so the first thing, easy peasy, that we're going to be talking about is what happens to waves whenever they hit a boundary. All right, and the big thing that you need to know is that whenever they do hit a boundary, they don't stop. All right, so you have two different waves. All right, so you have the wave that is going towards that boundary, and that's something called an incident wave. All right, so that's the original wave. Well, whenever it hits that boundary, it does not stop. It actually reflects, meaning it comes back. All right, so your reflected wave is going to be that wave that's coming back towards the origin. Okay, so we have two different types of boundaries that waves can hit. All right, they can hit a free boundary or they can hit a fixed boundary. All right, and you'll notice the difference. So both of these, the one that's hitting the free boundary and the one that's hitting the fixed boundary, both of them are going towards the boundary on the same side. They're both crests. All right, but if we look at that free boundary, all right, you'll notice that the free boundary, look at the second part and the third part, it allows that rope, that medium, to move freely. All right, hence the reason it's called a free boundary. All right, so because it allows that rope to move freely, that wave is not going to miss a beat. So whenever it returns, whenever it reflects back towards the origin, it's still going to be on the same side that it was whenever it came. All right, however, whenever you hit a fixed boundary, all right, so you see that you start as a crest right here, it hits that fixed boundary. Well, that fixed boundary does not want that medium to keep moving. All right, so even though it is going to reflect and come back, you'll notice that the reflected wave has been flipped. All right, so not only is it reflecting back, it's going to be flipped over the axis and it'll become a trough on its way back. All right, so at a free boundary, whenever they reflect, they're just going to be the same wave. All right, they're going to, if it comes as a crest, it's going to leave as a crest. If it comes as a trough, it's going to leave as a trough. But with a fixed boundary, as it reflects, meaning as it bounces back, it's going to be inverted. So if it comes as a crest, it's going to leave as a trough. If it comes as a trough, it's going to leave as a crest. Okay? All right, so that's relatively easy. All right, now here, this is one of the reasons why I don't love using my iPad for these. So if you had this up on a PowerPoint, you will see that there are words right here. There are words underneath this. So I want you to write those right now. All right, so we looked at what happens whenever waves hit boundaries. For the rest of it, we're going to look at what happens whenever a wave comes in contact with another wave. And that's something called wave interference. All right, so again, wave interference. Okay, sorry, I can't write and talk at the same time. Is just whenever two waves meet while traveling along the same medium. So it's when two waves meet while traveling along the same medium. Okay? All right, now whenever they meet, they can actually combine. All right, and this is something called the superposition principle. Y'all got to bear with me. Again, I can't write and talk at the same time. All right, so the superposition principle states that more than one wave can occupy the exact same place at the exact same time. All right, now think about what waves carry. All right, waves carry energy. Now think about what they do not carry, and they do not carry matter. All right, so that's the reason why they can exist in the same place at the exact same time. All right, so if you were standing in a certain spot, all right, nobody else could come and stand in that exact spot at the exact same time that you are standing there. It's because we're all made of matter, and two forms of matter cannot exist at the exact same time. At the exact same place. But because waves do not carry matter, they are not composed of matter, they can exist at the same place. All right, so whenever we have these waves that are being combined, all right, they're going to form another wave, a resulting wave. All right, and that's kind of what we're seeing. This is a video, all right, along with this one. All right, and I love this slide. So if you want to pull this up as a PowerPoint and watch this, it's actually so helpful. This actually goes a lot slower than this one right up here. All right, this one goes pretty fast, so you can't really tell what's happening. All right, but you'll notice that as these two waves, most of the time you have them coming from opposite directions. All right, but whenever you have a crest being added to another crest, or say a trough being added to another trough, because they're on the same side at the same time, they're going to combine and form an even bigger crest and form an even bigger trough. However, if you have waves that meet and you have a crest meeting a trough or a trough meeting a crest, that means that they are going to subtract from each other. All right, so you have the combining, so this would be like a +1, this would be a -1, +1, and -1. All right, well, whenever you have those two +1s combining, hey, that makes a +2. If you have those two -1s combining, hey, that makes a -2. But look at down here, we have a +1 and a -1 and a -1 and a +1. All right, because they are on opposite sides, and in this case, they are the same amplitude, we have complete cancellation. All right, our resulting wave would be just no wave at all. All right, so that's kind of what happens whenever we have noise canceling headphones. They're sending out the same frequencies that are coming in. So all of the sounds that are out there are being canceled out. All right, so whenever we talk about this building up that you see right here, this is something called constructive interference, and it's exactly how it sounds. All right, if you are in construction, all right, or if you are constructing something, then you are building it up, and that's whenever you have two or more waves that are on the same side. All right, so say in this A right here, we see that we have a crest going to the right and then a smaller crest coming to the left. All right, so we'll say this is a +2 and this is a +1. All right, well, they are going to come together like you see in B, and whenever they meet, they're going to add together. So the resulting wave is going to be an even larger crest with an amplitude of +3. All right, but once they combine, after they combine, you'll notice here that they just keep going on in their own separate directions. All right, they don't combine forever. They are just moving towards each other, and at that specific time, at that specific place, they add together on their path, but then they keep going as if they had never met at all. All right, and the opposite. So what you see right here, all right, you see the tearing down, the subtraction, and that's called destructive interference. All right, and destructive is happening whenever they are on opposite sides of that equilibrium position. All right, so here you see that we have a +2 again, all right, but it's meeting a trough, all right, a smaller trough. All right, so we have that -1. So as they are traveling, all right, you'll see they begin to meet, and then at C is when they combine totally. So if we combine a +2 with a -1, all right, we're going to form a +1. All right, so that new crest, it will be a crest because the crest was larger than the trough, but it will be a smaller crest than what we saw over here because of this negative. Okay, and once again, just like we saw in the last one, once they meet, they will just continue on their own little ways. All right, so say we have a wave of amplitude 0.3 that interferes with the second wave of amplitude 0.2. I want to know what is the largest resultant displacement that can occur. All right, so if we're looking for the largest resultant, that means that they are going to be constructive interference. They're going to be on the same side of the equilibrium. All right, so here we'll have our 0.3. And then over here, coming from the opposite direction, we'll have our 0.2. All right, so both of these are crests, so they're both going to be positive. So whenever they combine, they're going to form a larger crest that has an amplitude of 0.5 meters. All right, so we just add them together. All right, so our largest resultant displacement, our largest amplitude, will be that plus 0.5 meters. Well, what if I would have asked you for the smallest resultant displacement? That tells us that we're going to have destructive interference. So again, we have that plus 0.3 meters, but this time, instead of having another crest, we're going to have a trough, which would be a negative 0.2 meters. So whenever these two combine, it will still be a crest because the crest is the larger of the two, but it's going to be a very small crest of 0.1 meters. Okay, so hopefully that makes sense. All right, whenever they combine, you're going to combine them, but if they're on the same side, you'll add them together. If they're on opposite sides, you'll subtract them. All right, now the last thing, we're just going to introduce it in this unit. Whenever we get into sound waves, we are going to talk a lot about standing waves. All right, so a standing wave is a wave that looks like it's not moving. All right, so what you would actually see on a standing wave are pieces that look like they're just going up, down, up, down, up, down, up, down, up, down. And then you have these points between them that look like they're not moving at all. So this is what a standing wave looks like. All right, so even though it looks like you just have a wave, a single wave that is not moving, it's actually a result of two identical waves. All right, so two waves with the same frequency, the same wavelength, the same amplitude that are traveling in opposite directions, and they interfere, they combine. All right, so whenever they combine, these points that look like they're not moving at all, these are the points where you have complete destructive interference. All right, complete destructive interference. Now, what do you think is the difference between just regular destructive interference and then complete destructive interference? Well, here we saw just regular destructive interference. You just subtracted them. But here is where we saw complete destructive interference. And that happens whenever you have equal amplitudes, but they're on opposite sides of the equilibrium. So you have a crest and a trough of the same amplitude that are combining. All right, so those nodes are examples of complete destructive interference. The parts that look like they're going up, down, up, down, up, down, up, down, where you have that largest displacement, these are called antinodes. All right, so the antinodes are the parts that look like they are doing the moving. All right, but the way that they are moving is they're just moving up, down, up, down. All right, so it's not that they are just moving up, down, up, down. That's where you have constructive interference happening. All right, so you have those two waves, those two identical waves building each other up. All right, so you can have tons of different numbers of antinodes. And this is what we're going to be getting into with sound. All right, this is where we get into something called harmonics. All right, so this one, you see that we have one single antinode with two different nodes, all right, one on each end. All right, because there is only one antinode, this is called the first harmonic or the fundamental frequency. Okay, so we'll get into that later. All right, this one, you see that it has two antinodes with three nodes, and so that's going to be our second harmonic. All right, so this one has three antinodes, and it has four nodes. All right, so hopefully you're noticing a pattern here. There's always going to be one more node than there is antinodes. And however many antinodes we have, that's the harmonic that we are looking at. All right, so like I said, we are going to go into way more depth into standing waves and harmonics whenever we talk about sound. All right, but we do need to know that standing waves are a result of wave interference. So you have these two identical waves that are coming in contact with each other and have both complete destructive interference, which is where the nodes are, and then constructive interference, which is where the antinodes are. All right, so that's it for notes for today. We're going to do a little bit of practice with this. So if you have any questions, you know where to find me.